wrong due date for the first homework assignment. It was supposed to be Friday, not yesterday. So if you didn't get it turned in, make sure you get it turned in. I also forgot to set the late date penalties, so you can turn in like up to 2 days late after Friday and you still receive credit, but you lose 5% each day. So if you didn't turn in, get that in. Any questions before we get started to lecture? Yeah.
So the homework's now due Friday, and then Saturday, Sunday, are two penalties?
So correct, it's due on Friday, and you can submit up until Sunday. But if you submit on Saturday, you lose 5%, and then if you submit on Sunday, you lose another 10% for that assignment that you submit. So minus 10% on Sunday. Yeah. The quiz, quiz 1 is up. It's on Mimir. You answer questions on it based on what's there. It looks something like this. Let's make sure I don't show anything. One thing that I forgot to note is you are not allowed to use bin, hex, or int in your solutions. Doing so is considered cheating. So, for example, you'll be asked a question like you have a custom bag of M&Ms. Each of your M&Ms in your custom bag can be one of 17 possible colors. What's the minimum number of bits you would need to represent the colors contained within your bag? So you would say, figure out whatever your number is, and then you would return whatever your answer. So if you thought it was 53, right, you'd put in 53 there as your answer. Say run test, and you'll see whether you get the answer right or wrong or not. Right, so we didn't use hex, bin, or int here, so that passed, but our answer was wrong. And there will be like different problems that you have to do, like convert this binary string to hex, and then show what the answer is supposed to be. Yeah?
Some of the questions don't have test cases.
Yeah, I think Trevor fixed most of those last night.
I saw the post for it, but it might have just fixed that one student, and then I tried commenting, but mine wasn't fixed afterwards.
Let's see. You know what the number was?
I think one of them's like number 5, and then another one's like 20 something, 22.
Well, 5 looked like it had something. They all have test cases, it looks like. Yeah. No, I appreciate that because, some things do get messed up.
How many times can we try the quiz?
You can try each problem as many times as you feel like.
Just before the due date?
Yes, before the due date. Oh, yeah, the light? Thanks. So one of the problems looks like it might have some issues already that I thought I fixed but didn't get fixed. But I'll take a look at that and see what's going on, if I need to fix it or not. Okay, so last time we left off, we were talking about the CPU. We talked about what it's made up of, the various components that are inside there. There's the ALU, which carries out the arithmetic and logic. There's your data registers, which temporarily hold values for you to operate on in the future. You have your connections to the address bus and data bus. The PC keeps track of which instruction you're on. It has the address of the instruction and memory you're working on. The stack pointer points to the top of this program stack. eFlags has various random bits of information about the current program that's running, like whether the result of the last operation was 0 or not, or whether an overflow happened or not, or whether it was a carry or not, or if you're in kernel mode or whether in your user mode. So just random bits of state there. And not shown here is the instruction register, which also has the actual instruction, whereas PC again has the address of the instruction. So we might think that, computers are pretty complicated machines, and in some ways they are, but in some ways they're very dumb and very simple, but just really, really fast. So the CPU, what it does is it just follows this cycle over and over and over and over and over again until you finally turn it off. So the first thing that it does is it fetches the instruction pointed by the PC from memory and places it into the instruction register. So the PC tells us what instruction we want to work on. So we go out into memory at that location, grab the instruction, and pull it from memory into the instruction register inside the CPU. So we fetch the instruction. We then decode the instruction, figure out what it does. So are we supposed to be adding, subtracting, multiplying, dividing, comparing two things together? Figure out what we're supposed to do. Then we do that thing, right? We do the addition, the arithmetic, the logic, or we do like subtraction, multiplication, division, whatever it happens to be, and then we write the result back either to the register or memory. And after we do that, we go back to step 1 and we get our next instruction. And then we do it all over again, over and over and over and over again, until finally, you turn off your computer. Any questions here? So sometimes it's useful to figure out the CPU speed, or like your computer speed, and there are two different ways of measuring it. There's the CPU time, which is the amount of time it takes for the amount of time the CPU actually spends working on your program. And then there's the wall time, which is just the actual amount of time it takes for your program to complete. Those two things are not necessarily the same, because the CPU might not always be running your program. It might be taking turns running other programs that take time. The CPU might also have to wait on other things like user input. And while it's waiting for user input, it's not executing your code because you're waiting for the user to do something. Or it might have to wait for like requests for different I/O systems to give it information. And while it's waiting for that information, it's not running. So it's not counted against your CPU time, but it's going to take more physical wall time for it to complete. If you want to figure out how long the CPU is going to take for your program, or at least a rough estimate, is you take how many instructions you have in your program, right, and you multiply them by the time it's going to take to carry out those instructions. This can be broken down because each instruction takes some number of clock cycles. So we multiply it by the clock cycles per instruction. So you might have like your add instruction takes 3 clock cycles. So every add you pay 3 clock cycles, but each clock cycle has the same amount of time. So you multiply it by the time per clock cycle. The clock cycle is generally what you see reported as the speed of your CPU. So like 3.2 gigahertz or 3.5 gigahertz or 2.7 gigahertz. That's how fast your CPU is. That's how many instructions it can do in 1 second. So that means if you had a 3.2 gigahertz machine, you could do 3.2 times 10 to the 9 cycles per second. And so if each instruction only took 1 cycle, you could do 3.2 times 10 to the 9 cycles or 3.2 times 10 to the 9 instructions per clock cycle, assuming your computer wasn't waiting to do other things. One of the problems, though, with trying to make CPUs faster is that if you try to decrease one parameter, it makes the other one go up. So if you try to decrease the number of clock cycles per instruction, what generally means is that each clock cycle the clock cycles have to become longer to still get the amount of work done. But if you're able to take more clock cycles, you can generally shorten the length of a clock cycle. But it's kind of like playing with the parameters and messing with them a little bit till you get it so you're actually going faster and not actually going slower. Wall time, again, you just time it. You press start your watch, wait for it to finish. When it stops, that's the wall time. Really, this is like the best thing to consider when you're actually buying some new computer. You'd like to run the applications on it that you're probably planning on running and figure out how fast it's going, right? Does it play the game that I want to play well, right? Is it going to be able to process, these really intensive, parallel programs really well, if that's what you're doing with it, right? And, you don't want to spend more money on something than you need. So if all you're doing is word processing on your computer, you can probably buy something a lot cheaper because you don't need all of that extra speed and all that extra power that's provided by the more expensive machines. Any questions? One possible way to increase the speed of your CPU is through parallelism. Parallelism is just doing multiple operations at the same time. There tend to be 2 different forms of parallelism. The first is pipelining, which is if you break down a sequence of things into multiple stages, and you do each stage you're doing a different thing. The common analogy that we give here is imagine doing laundry, right? When you do laundry, you don't wash the first load, then dry it, then fold it. Then get your next load of laundry, wash it, then dry it, then fold it. Then the next load, wash it, dry it, fold it, right? While you're washing one load, right, you're drying the other load and folding the load of laundry that just came out. And if you assume that each of those stages was roughly the same, you'd get about a 3 times speed up. To kind of visualize this, come on. right? With the slow way of washing, drying, and folding, right? We might have wash, dry, fold, wash, dry, fold, wash, dry, fold, wash, dry, fold. Right? And I guess you'd probably actually start. That's going to take us about like 11 time units to complete, right? Assuming each stage was the same, right? And we were able to do 1 load of laundry, 2 loads of laundry, 3 loads of laundry, 4 loads of laundry. I guess I have to go up 1 more. But if we were doing this the intelligent way, right, we would do wash, right? And so we start washing. And then during the next time unit, since we're done using the washing machine, right, we can start our new load of laundry. And then we can start drying the old load of laundry that just finished out of the washing machine. Then we get to the next one. We can have now wash, dry, and fold. 3 of them at the same time. Wash, dry, fold. Then we're just going to have dry, fold, and then just fold. And that was 1, 2, 3, 4 loads of laundry. Right? But how much time did it take? Right? It only took like, 4-ish units, or 5-ish units, right? Compared to our 12-ish units. So since we have 3 stages, we got about 3 times the speed up. Right? We finished in about only a third of the time, right? About 4 units. So that's one of the advantages of using pipelining and breaking things down, right? This is also what like Henry Ford kind of discovered when he started like the assembly line, right? You have multiple people doing their own individual task at each certain stage, and you get things done a lot faster. So the hardware system automatically does this for you. So instead of washing laundry, right, we execute instructions. So while we're fetching one instruction, we'll be decoding the other instruction, we'll be executing some other instruction, and writing the results of some other instruction that went along the way, right? So we can hopefully get like a 4 times speed up if we do it that way. There are some practical limits to this, like if you start making your pipelines really, really long, you don't get like an end time speed up all the time, because a lot of the times you end up not being able to do work every single clock cycle in each stage. This is because of things like if statements, right? You don't always do the same work every single time. So you might have to wait to figure out whether you do that going to the if statement or going to the else statement to figure out what your next instruction should actually be. And so you have some delays that are showing up in there. Right? So you're going to get that worse performance if the pipeline isn't kept full. So there are some practical things that make it so we can't have like 50 stage pipelines and have our computers go 50 times faster. They tried. It didn't work well. The other type of parallelism is parallelism you write into your own machine. There's 2 major paradigms, which is message passing and shared memory. In message passing, processes explicitly send messages to each other, and you might wait to hear for some message before you continue on with your next task. Or there's shared memory where there's a shared area of memory where the processes will write into that area to communicate to each other. This can be very challenging to do correctly and efficiently, but it's really important to consider if your data sets get very large, because hopefully if you're able to have like n processes working on your computer at a time, you'll get an n times speed up on it. The problem is, like you've probably thought about, like when you work on homework assignments with your friends, right? If you just keep adding more and more people, does the process keep going faster and faster and faster? No, what slows you down? If you keep adding more people to a group. I mean, you're kind of on the right track about like introducing each other, but there's that communication, right? You might have to wait for your friend to finish doing something before you can finish working on your part of the project, right? Or vice versa. Or there might be some parts of time where you guys all have to stop working just to talk to each other to figure out what you want to do next. So even though you might keep adding more and more people, you're not going to be able to go faster and faster and faster, because you probably spend more and more time communicating with each other. right? And so there is an overhead for that, and that does actually show up in parallel programs, where you do end up going. You may have to like not be able to get that full times and speed up because you have to wait for the processes, one to finish the task or for some other one to talk to some other, for one process to talk to another before you can move on. The sad thing is also you have to write this, and a lot of times when we focus on algorithms, we assume that there's only one unit doing the work. And so you can do like a lot of optimizations because you know that only one person at a time is working on it. But when you start splitting up tasks, you might have to use more naive and simple and more expensive algorithms and not be able to do those optimizations because the problem's been broken up and not everyone can see everything at the whole time. But there are some problems that are like really, really good for parallelization. They're called like embarrassingly parallel problems. For example, like matrix addition is an example of an embarrassingly parallel problem, because when you compute like Cij, right, Cij is equal to Aij plus Bij. There's no like communication that needs to go overhead for figuring out what the value is for one new cell, right? So if you split it in half, where I'm going to do the top half, you do the bottom half, we don't have to talk to each other at all as soon as we figure out what part we're doing. Or if you want to split it into thirds, great, no overhead. And so you should hopefully get that full 3 times speed up. If you're interested in working on this, this is what like the concurrent programming class is all about.
Split it up into n chunks.
Yeah, you split it up into like n chunks to do work. And a lot of times with modern computers, you do have more than like one core or more than one processor in most of your machines nowadays. So if you're able to exploit that and utilize it, right, you're able to solve problems faster. And you guys might like be like, what's the point? My computer's already blazing fast. Well, that's because most of the problems that we have you do are simple problems, small problems, right? We're not giving you 1 million elements to work on, right? Or 2 million. But when you're somebody like Google or somebody like Facebook or Amazon, right, they deal with huge volumes of data. So they want to be able to go as fast as they possibly can. And a lot of times those transactions tend to be independent, so they can exploit the parallelism of the problem to be able to not take forever to get stuff done. Okay, any questions before we move on to assembly programming? So I will let you know that if you go to the Google Drive and you go into assembly, you will find this Intel cheat sheet. This pretty much has like everything that I know about programming in assembly. So like if you want a quick lookup about stuff or what you need in this class, look here. The book is also a really good source of information as well. It's probably like one of the best things I've ever been able to find on assembly programming. And so if you start looking online for help, you're not going to find anything really. Or if you do, it'll be worse than what we've already given you. So if you're struggling with the assembly, make sure you come see us. Make sure you check out the resources we provided, because unlike C or Python or Java, nobody really programs in assembly. So there's not much, you're not going to really find anything on Stack Overflow for help, or anywhere else on Google for that matter. So let's talk about our instruction setup. So most of the instructions that are written in assembly have this form: operation, destination, source. So there's 3 components for each instruction. The op part tells you like what you're doing. Am I doing adding? Am I doing subtracting? Am I doing multiplying? Right? Am I doing dividing? Am I doing shifting to the right? These are all various instructions that you've seen. The effect of these operations, though, are always going to be, for the most part, dest op equals source. So all of the operations for Intel are pretty much written in a 2-operand form. So they're always going to be like plus equals, times equals, divide equals, minus equals. There's never just going to be minus. It's always minus equals. Or plus, it's always going to be plus equals. So when you write your code, you have to pay attention to that. Again, this is what's referred to as a 2-operand machine. There are other languages like MIPS. MIPS is a 3-operand machine. And their formats are something like operation, destination, source 1, source 2. And so with the MIPS machine, you'd see something like the destination is equal to source 1 op source 2. But again, Intel has a 2 operand machine. So like adding, right, if we did add AB, this is equivalent to doing A plus equals B. For subbing A minus B, for AB, this is going to be like A minus equals B. Any questions about that so far? It's just going to have to change like how you write your code a little bit when you get into assembly, given that everything's like plus equals or minus equals. For the most part. There are some rare exceptions to this. Okay, so what can your possible operands be, right? These guys over here are your operands. So what are some options? One option for your operand is constants. So constants are prefixed with dollar signs. So if I did something like movl $4, and then I'll show you the other one, to EAX, that would say put the value 4 into register EAX. Right? So constants have dollar signs in front of them. If you forget to do the dollar sign in front of them, you're going to get segmentation faults in your code. Because without the dollar signs, it specifies an address in memory. So this guy right here says something like move the value 4 into register EAX. Whereas if you did this, move L4 to EAX, it says move the value at location 4 in memory into EAX. So if you don't do the dollar sign, you are going to have the problem of accidentally accessing memory and reading from memory. The registers that you have to work with are over here in the cheat sheet. So here are your registers. They're EAX, EBX, ECX, EDX, ESI, EDI, EBP, and ESP. A through D, so EAX through EDX, and ESI and EDI, these are all general purpose registers. So when you get to your first assembly programming assignment, feel free to use them for whatever you feel like. Those are the ones that you have access to, though. EBP for your first homework assignment, you can use it as the base. It's used as the base pointer C code. We'll talk about what that means later. But if you're using it for standalone code, you can also use it as another general purpose register. ESP, like we talked about earlier, is the stack pointer. Don't use this one as a general purpose register. It's going to mess you up, right? Because the stack pointer needs to point to the top of the stack. And if you start putting other things into it, it's probably going to start breaking some other code. So don't do that. When you want to access a smaller portion of a register, you just leave off the E, right? So the first four, A through D, there are smaller subportions. If you want to access the entire register, it'd be something like EAX. If you only want to access the lower 16 bits, that's AX. If you want to access the upper 8 bits of AX, that's AH, and the lower 8 bits of AX, that's AL. So the division looks something like this. So if here is our register, I guess, let's see, where's the merge thing? So this guy over here would be, we probably want to, so this right here might be something like AL, and then AH. Taken together, these are AX, and then all four of them would be EAX. So that's how it's broken down. And you can do this with EAX, ECX, EDX, EAX, EBX, ECX, and EDX. You can't do this with ESI, EDI, or EBP, or ESP. Only A through D. I know it seems kind of weird, and a lot of you guys are like, well, how do I access these bits up here? You can right shift it, and then put them into the lower portions, and then access those bits if you really wanted to get the upper 2 bytes of memory, or upper 2 bytes of the register. But for the most part, we're probably only going to be working with EAX, and sometimes we'll be working with AH and AL if we're dealing with characters, because characters are 1 byte big, while integers are 4 bytes big. Also, when you're working with your registers for your operand, registers are prefixed with %. So if you actually want to reference EAX, it's going to be %EAX. If you want to talk about DX, it's %DX. If you want to talk about CL, it's %CL. Right? But registers have to be prefixed with a % sign in front of them.
Question? So what is register?
So a register is memory inside of the CPU. There's a very small amount. You can see there's only like 6 or 7 registers. But that memory is very fast to access, and it's inside the CPU, which also makes accessing it fast. So if you're trying to look for like optimization and like improving your code at its efficiency, you want to do operations with things in registers as much as possible instead of having to go to memory, because going to memory is going to take longer.
So is it like a container inside of the memory?
Say it again.
So is register a container? It stores data.
Yeah, registers do store data, right? But instead of being like your RAM, your memory that you buy for RAM chips, it's inside of the CPU. So it's small, fast, internal memory inside of the CPU. And a lot of times it's used to temporarily store the results of computations while you're working on them. And then you write them back out to memory. So at this point in time, this is when you actually are going to need your Linux system, because our code's not going to work anywhere else. So if you haven't gotten access to a Linux system, now's the time. There's a question up front?
If you have a AMD processor, does it matter?
AMD will be fine because AMD they've cloned the Intel instruction set. So Intel instructions work on AMD processors, even if the internal implementation is different. No, that's not what I want. For some. Okay, that's where I want to go to. Yeah, I'm going to 1 second. It's semi. No. Oh, it's CD into some list. Does that seem big enough? Like this? Larger than that? We'll try this. Does that seem big enough? Okay. Oh, that's right. I gotta figure out how to turn. I've forgotten where the option got moved for changing the highlighting. So anyway, for right now, we're going to have to look at it be ugly black and white because I don't remember where the, is it view? Highlight mode. Oh, there we go. There you go. Now you get it nice and pretty. Oh, we're over here. So this program we're going to walk through to kind of give you a better idea of how the assembly code goes. But here's our program that we're trying to build from C. And I recommend whenever you're writing your assembly programs for your homework assignments, you always write the C code first. The reason I recommend writing the C code first is that it's much easier to debug C than it is to debug assembly. When we get into assembly, we don't have variables anymore, right? They're all gone. We just have registers to work with, and we have to keep track of a lot of things in our own mind and in our comments too. So remember what's what and where things are at and what that thing's supposed to be. Whereas when you're working in the higher level language like C, even though C might not seem high level to some of you, you're going to still have the variables, you're still going to have the functions, you're still going to have access to like the debugger, and there is still a debugger here as well that you can use. But it's just going to be so much easier to figure out the problem in C, and then once you get the problem down, you can then translate it into assembly. And I will show you steps later on that are just like, here's the steps you follow to turn a for loop from C into assembly. Here's how you translate an if statement in C into assembly. So it's going to make your life a lot easier if you follow along. But this is our goal, a very, very simple program, and you're going to see that it's a lot more. So first, you're going to see some lines that start with dot. The dot are like pre-assembler directives that are similar to like the preprocessor directives in C and C++. They're going to be run before any of the other lines of code get executed. So like pound define or pound include, they're similar to those, but they start with dot. There's dot global. Dot global means make this symbol visible to the linker. And what that just means is it makes this symbol available outside of this file, and you can access it from other files as well if you have a multi-file program. Underscore start is basically main. Underscore start is where your program starts at. And so the linker needs to know where to begin execution of our program, so I need to make it global. The .EQUs are the equivalent of pound define in C. So I'm saying define the symbol word size to be equal to 4. Define the symbol xlen to be equal to 10, right? So now everywhere the assembler sees the word size, it's going to replace it with 4. So word size is 4 and it has no difference. From 4. Xlen is 10. Everywhere the assembler sees xlen, it's just going to replace it with 10. Now, here you can see me trying to be fancy, but I wouldn't recommend doing this, is we could define a registers to be equal to some kind of like variable name. So now every time the assembler sees sum, it's going to replace it with EAX. So I can kind of treat sum like a variable and give it a name instead of always thinking about it as EAX. The problem with doing this is it's possible to assign multiple registers to the same, multiple variables to the same register. So on the next line down, I could say like .EQUI %EAX. Now EAX is both I and sum, but really there's just one register, EAX. So if I put something into I, it's going to change what's in sum. If I put something into sum, well, that's EAX. It's going to change what's in I. right? It's just allowing me to create this alias for the register, but I wouldn't recommend doing it. I should also mention back here, I don't think I made the point, but there is just one 32-bit constant or 32-bit field here for EAX. So if you change AH, you change AX and you change EAX. If you change AX, you change EAX and AH and AL. If you change EAX, you change AX and AH and AL because they're just sub-portions of the same register. Does that make sense? There's just one EAX register, but you can just talk about different parts of it. Do I want to talk about these 8 bits or these 8 bits or these 16 bits or all 32 bits at once? But they share that same location on your chip.
When you change, let's say AL and then you shift it to get the upper 16 bits, does that also change the lower AL bits?
Yeah. Right? I mean, like, well, let's say, like, if you're shifting AL, all the work is done inside of AL. So if you did something like shift right percent, shift right $3 percent AL, it will only change AL. The contents of AL will be moved to the right by 3 bits. But you're not going to get anything from AH coming into AL. But it would modify then what like AX is and EAX was from doing that operation. So there are 2 major sections, and as you probably figured out, comments start with hashtags. You can also do multi-line comments by doing /**/*. So there's 2 main sections. There's the data section, and there's the text section, right? You guys probably might have heard those names before, at least vaguely sometime in the past. The data section, once again, is where our global variables and our static variables are going to go. And the text section is where our program's instructions go. So over here in my data section, I'm making something what's called a label. And a label allows us to give symbolic names to addresses in memory. So once again, a symbol allows you to give symbolic names to an address in memory. Right? So X, right, it might be at location 100. And now every time I say X, it just gets substituted as 100, but I don't actually have to remember that X is 100 or what its actual address is. The linker will take care of that for me later on. So over here, I'm trying to create essentially our array, and you're seeing a new preprocessor directive, which is .rept. So .rept says repeat the code inside of the body up until end rep xlen times. But the xlen, or the value here after .rept, it has to be a constant, right? And remember, xlen is just 10. So writing xlen here or writing 10 here, there's no difference. But this value has to be a constant, right? It cannot be some value of some register. So you can't say EAX. That's not going to work. So over here, what I'm trying to do is make space for our array. And there are a couple of different ways that you can say to make space. .long is used to make 4 bytes worth of space, and it gets initialized to this value on the right-hand side. When you're writing constants, let me say that again. When you are writing constants, and only constants, in assembly, you can use the C-style notation for the arithmetic. So I can do 5 times 2 plus 2 to get 12. Right? I can do, ANDs with 3, XORs with 7, minus 90. Right? The expression here can be as complicated as I want, but it can only be used to create constants, and everything in here must be constant. Does that make sense?
Do you need to add $sign?
So here, when you're working with the preprocessor directives, you do not use $signs. The $signs only show up in the instructions themselves. So preprocessor directives, no $signs for the most part. When you're in the instruction itself, $sign to denote the constant. Any other questions before we keep going?
Why is it 12?
5 times 2 plus 2 is?
Right. Like, why do you use 12?
I just picked a number. Right? So I'm making an array of, 10 12s. Right? But I wanted to show you that you can do some, crazy math stuff here in the C style if you want to. There are other ways of making space as well. So dot byte makes a byte. Dot word makes 2 bytes worth of space initialized to value. Dot long, 4 bytes worth of space initialized to a value. Dot float value, 4 bytes worth of space initialized to some floating point value. Dot string val, you write some string, it will make the string null terminated, and it will allocate that much space that it needs to fit it. And then there's dot space n, which just makes space for n uninitialized bytes of memory. So if you do dot space 16, you'd make 16 bytes worth of space. So these are the basic ways of creating space in the data section, right? And we're using int or dot longs for integers because integers are 4 bytes big. So that's why dot long comes into play. So dot text, this is the beginning of our program. We're actually going to begin the execution. And again, our programs always start at underscore start. Always start underscore start, and there can only be one underscore start per program. And again, the labels are followed with colons. So x colon, underscore start colon. The naming conventions for symbols are essentially the same things as the naming conventions for variables. Alphanumeric strings that don't begin with numbers and can have underscores in them too. Over here, you're going to see me using some comments to help remind myself of what I'm doing for each register. So EAX is going to hold the sum, and ECX is going to hold the count. I highly recommend you do this because, again, there are no variables. So if you don't leave comments to yourself about what you're planning on doing, you are going to forget when you come back the next day what register was playing the role of what variable from your C code. So the first thing that we do is we initialize our registers. So we set sum and I both equal to 0. So here we have the move instruction, and each of the instructions has a suffix, and the suffix denotes the size. L is for long, so these are 4 byte quantities that we're working with. W stands for word, and they're 2 byte quantities. And B is for byte, a 1 byte quantity. Right? So you prefix the instruction with how big is the thing that you want to work with. So over here, since EAX is a 4 byte quantity, I'm going to use L. So set EAX equal to 0, set ECX equal to 0. Again, registers prefixed with percents, constants prefixed with $signs. And move just moves the value. So move source into destination. Right? Source dest. So here we have our label for beginning our for loop. And the weird thing, I guess, about assembly in terms of the comparisons with Intel is all of your comparisons are going to be against 0. Does that make sense? So whenever you have some comparison, it's always, is this thing greater than 0? Is it less than 0? Is it equal to 0? But it's always 0 on the right-hand side of your comparison. So when we started with our code, right, it was, is I less than xlen? So did we have 0 on the right-hand side? So I less than xlen is 0 on the right-hand side of that expression. No, so we're going to have to rearrange our expression so that it ends up being compared against 0. So what we do is we just subtract xlen from both sides. I minus xlen is less than 0. Now 0 is on the right-hand side. The other thing is these jump instructions, they're taken when true. Right? So if this, what this guy is saying is jump to the end of the for loop if the result of the last instruction was greater than or equal to 0. So with while loops, right, you want to go inside the loop while the condition is true. Right? Like while the condition is true, you keep doing the code inside the for loop or the while loop. But I like to invert the conditions and say get out of the loop if you're not supposed to be in there. So all of my loops that look like, this, like while some condition, right, do stuff, I change them to be this. while true, if not condition, break. Would you agree those loops do the exact same thing? Besides that, we have the do stuff here. Would you agree that both those two while loops would do the exact same work? Are there any questions or confusions about that? So they are equivalent. So I end up doing the exact same thing with my code when I'm writing it. So over here, right, our original condition was I minus xlen, is that less than 0? So the opposite of this condition is it I minus xlen greater than or equal to 0? So over here, I'm going to compare L, again, $xlen, it's the constant, against our I, ECX. If ECX minus xlen is what's going to be computed here. But when you do the comparison instruction, it's one of the few instructions that doesn't store the result into the destination. I think I put this backwards over here. This should be source and then dest. And then these ones should be the other way around. B plus equals A, B minus equals A. So comparison is just comparing the values, and the way that it compares the values is through subtraction, but it will not store the result of the subtraction into the destination register. So here we do ECX minus xlen, right? I minus xlen. And if that result is greater than or equal to 0, go to the end of the for loop, right? Finish up. There are other types of comparisons, like what do you think greater than is? JG for jump if greater than. What do you think less than is? JL, right? Jump if less than. Jump if less than or equal to? JLE, right? Jump if less than or equal to. For equal, JE or JZ, jump if equal to, or jump if 0. There's also ways of specifying signed versus unsigned comparisons, which if you look at the cheat sheet, it goes through that there. So here, right, we have our comparisons. So like we have jump if less than, jump if greater than, less than or equal to, greater than or equal to. But there's also jump if below. Jump if below is like the less than comparison, but for unsigned numbers. Whereas jump if above is greater than for unsigned numbers. To give you an idea of why we need two instructions, answer the following question. Which of these is bigger? So which value is larger, the top one or the bottom one? Top one is larger. Bottom one is larger. Why do you say the bottom one's larger? What's its value? Well, if it's an unsigned number, what's its value? We have 1 plus 2 plus 4 plus 8, that's 15. And 15, is that greater than 1 plus 2, 3? Yes, but what happens if we interpret the number as signed numbers? The first number is still 3, but the second number is -1. So which is bigger, 3 or -1? 3, right? So it depends on how you're interpreting the bits, right? They could mean one or the other. It just depends on the context of your program, right? And that's why there's these two types of comparison instructions. So if we were treating these numbers as being unsigned numbers, we would use below and above for less than and greater than when comparing unsigned numbers, right? If they were treating them as signed numbers, we'd use less than or greater than, JL, JG. Does that make sense? Any questions so far? Don't worry, we'll get you writing assembly code in a minute. So over here, so it says, if the negation of the condition holds, break out of the loop. Go to the end of the for loop, and then we're going to be done. This line of code over here is an access of memory to read an array. And the way that this expression works is that there is 4 fields, D, O, I, and S. Displacement, offset, index, scale. And we will definitely talk about this a lot because everyone always gets confused here every year. So what this does is it takes the displacement, adds the offset to it, then adds the index times the scale together, and then you go to that location in memory and get the value that's there. Right? There are some constraints, and again, we'll talk about them in a little bit, but the displacement field needs to be a constant expression. O and I both need to be registers, and scale can be either 1, 2, 4, and maybe 8 on 32-bit machines, but 8 definitely works on 64-bit machines. I just never really had the need to try out 8. We'll go through that one a lot more in detail. But if we think about our memory access back here that we're trying to emulate, sum plus equals x at I, how can you rewrite x at I without using the square brackets? So sum plus equals, how can you write that expression without using square brackets? It's star x plus I, right? So we want to go to the location of memory at x plus I, right? And down here, well, what's this thing going to do? Well, it's going to give us something at memory at D plus O plus I times S. Now, if you don't give one of the fields, it's going to default to be 0. So over here, right, I have x plus 0 plus ECX times the word size. And if you remember, word size back here was 4, and you're going to see me do like word size or WS on every single problem. So I don't have to keep remembering that it's 4. Now, one thing that we didn't have to do back here was just x plus I, right? But if x is an array of integers, we want to move I integers past x. And the compiler is nice enough for you when you're in C to take the size of the variable and multiply it by how big you want to move. But when you're working in assembly, you have to do that yourself. So over here, I want to move I integers, each integer being 4 bytes big. So I have to do ECX times I, or times word size, to get the right amount of integers to move. Because memory is always byte addressable. So every address you generate in assembly is always going to be which byte do you want to start reading from. So for us over here, we need to make sure that we multiply by 4. If we were dealing with shorts, this would have been 2. If we were dealing with bytes, it would have been 1. So like chars would be 1. But you have to be responsible for doing that multiplication yourself now. So we get the value at x at I, and we add it into EAX. So we do that addition. So EAX, right, which is our sum, plus equals x at I. Then we increment ECX to go to the next iteration of our loop. That's our I++. So the reason you have plus plus or I is because there's an increment instruction, which increment just means add 1. So I add 1 to ECX, and then I go back to the start of the for loop. Any questions before we run it? Yeah.
What is this group in C code?
These lines.
Can you find this file on drive?
Yeah, it should be there. Yeah.
So what if I write C++ instead of C before I write something? Will that be helpful?
So the question is, if I write C++ before I write C, will that be helpful? It depends what construct you're using in C++. If you're doing things like with vectors and maps and like really high-level things, it's not going to be worthwhile because now you're responsible for translating the vector code into assembly code, right? Because that's the code that you wrote. Or if you're using maps, you now have to implement the map code in assembly code, which is going to be pretty hard to do. The reason I recommend C is because when C was written, it was written by people that were programming a lot of assembly, and so they kind of based their instructions to be based the syntax of C, where the translation between the C code and the assembly code is very easy, right? There's not a one-to-one correspondence, but it's somewhat close for an operation. So it'll be more helpful if you do C and you do things like arrays and dynamically allocate memory. If you have to do that, because that's what you'll need to be doing in the assembly, and it'll be a lot easier to do those things than to do C++ stuff.
Thank you.
Yeah.
What is OUDOIS?
The O stands for offset, so displacement offset index scale. And again, we'll get more into that one in a minute because that's something that we use a lot for accessing arrays. And we will definitely delve into that syntax. So let's try running our code, which first means I probably need to save it. Oh gosh. I think I just save it a second time. Or maybe I just copy it somewhere else. Okay, this one got saved. And so there's a two-step process if you want to compile your assembly code. The first is to assemble it. So it's going to be as-gstabs-o, the name of the object file you want to create. So I'm going to do forsum.o, and then the source file, forsum.s. Assembly files start with .s. So we've now created our partially compiled file. Sorry, let me put that back up there. We've now created our partially compiled file, forsum.o. We now have to go run that through the linker. So it's going to be ld. Oh wait, I think I forgot something. Since we're doing 32-bit assembly, it's a --32 to do with the 32-bit compile. Because all of us are going to be on 64-bit machines, but we're going to want to do 32-bit compiles because we're doing 32-bit assembly. So --32 for the 32-bit compile. Then for the linking, it's ld, and then it's -m_elf underscore I 386. And then the name of your executable, -o for some.out, and then the object file, forsum.o. Hopefully I remembered that one right. Good. This part here just says link for 32-bit Intel architecture. Intel, i386. So just remember that business for when you're doing it on your own machine, because otherwise you're going to get some fun errors. Now we have our executable, and let's try running it. And it's going to crash. So all the code that we're writing right now, it will 100% crash every single time. So what we're going to have to do is run it through the debugger. So for those of you that have been avoiding the debugger, you now have to use the debugger. My preferred debugger is DDD when I'm debugging assembly code. So DDD, and then my executable, forsum.out. The --gstabs is equivalent to like the -g when you're compiling with GCC or G++, and it will actually allow you to debug your code. If you forget to do this, when you go to debug your code, there won't be any code for you to look at. Now, from what I can remember, I don't know how to make the text here any bigger. So what, zoom in? I don't know if it's going to let me zoom in. Nope.
Question.
Yeah.
The DDD comes with limitations.
Say it again?
The DDD is another code with limitations.
You probably won't have it, but you can use, if you don't have it, oops, not this one. If you don't have DDD by default, you can run sudo, oops, clear. You can run sudo apt-get install DDD. And this will install DDD on your machine. And I spelled sudo wrong. It should be sudo. It'll ask you for your password. I typed in my password. And I already have it installed, something happened, but it'll install it on your machine if you don't. So DDD are executable. Run it in the background though. I don't know. We'll try seeing if this makes anything bigger. Oh, come on. I don't think that changed anything. So sorry about it being tiny, but that's what we're going to have to deal with. And I don't know how to zoom in. Oh, I think I remember what I did. I do view. Oh, that's fun. Okay, I don't think I can actually use that. Because I can't see anything. But anyway, in terms of commands for setting breakpoints, and one thing I forgot to mention is that back here, right, there's this symbol down here, done. Done is not special, but you'll see it pretty much at the end of my programs, just so that I know where I can set a breakpoint to be at the end of my program. So underscore start, it's special. Done is not special. It does nothing. The NOP stands for no op, and it means don't do anything on this line of code. So do nothing. It's like pass in Python. Do nothing here. No operation. Back to DDD. So what I'm going to do is I'm going to break, and to set a breakpoint, it's B and then underscore start to set a breakpoint at underscore start. And then I will also set a breakpoint at done, so B done. The other way that you can set breakpoints here is you can right click on the line and then select set breakpoint, and it'll set a breakpoint there. To be able to display registers, there are a couple of ways of doing it. So first, let's start our program. So to start your program, just type R or run to make it start running. And to see the registers in DDD and in GDB are prefixed with $. So I'm going to say graph display $EAX. And I can see what's in register EAX. I can also say graph display $ECX to see what's in ECX. The other way that you can see this is go to status registers, and it will show you what's in the registers. So over here, if we start stepping, which is S to step a line of code, you can see that we put 0 and 0 into ECX. We now pop down all the way here to our line of code, and we're going to compare ECX with xlen. So after we subtract ECX from xlen, will that result be greater than or equal to 0, given that ECX is 0 right now and xlen is 10? 0 minus 10 is negative 10. Is that greater than or equal to 0? No, it's not, so we're not going to take the jump. We're going to go into our for loop. Now we need to do this addition. So let's say we actually want to be able to display this array. It's a bit complicated, but I will show you the syntax. So here it's graph display. And what we have to do is we have to, because like x has no type, we have to give it a type through casting. So that's going to look like this: integer pointer, and then the address of x, and then I can say I want to start at 0, and then at 10 to see all of the elements. And that'll print out all the values. If you look over the debugging slides that are available on the Google Drive, you'll see all of these commands there as well. So if you're not catching them at the moment, look there. If we want to just display ECX or display x at I, we can get rid of the at 0 or at 10 here and replace this with $ECX because that's our I. And now we can see what's our array of x at I. Now if we keep stepping, we're going to do our addition. So we should see that EX is going to change and EX should get 12. If we keep stepping, the jump will be taken. So we go back to the top. We do our comparison. The condition won't hold true yet. So then we're going to add our next 12 and we get 24. Then back around again. And then we don't take the jump. And then we add our next 24. And so on and so forth as we keep going. Now when we continue, we'll go all the way down to our next breakpoint. Continue is just C. Or again, you can use these buttons over here on the right-hand side. And we've reached the line of code for done. And we've gotten 120, which makes sense because 12 plus 12 10 times is 120. But now notice that even though we've reached done, our program hasn't stopped yet. So if we keep going, we go out of the bounds of our program and we keep executing code, and eventually we're going to do something that causes a seg fault. And it's going to break our code, which is why you can't run your code outside the debugger. Also, you can't use any print statements because printing is really hard in assembly. And you are more likely to screw up in calling printf than you are to get the call to printf right and most likely introduce more bugs into your code. So you absolutely 100% have to use the debugger for your next homework assignment, and probably all the homework assignments that are coming after this. So if you're still struggling using the debugger, come to office hours, get help. We'll help you walk through it, but you're going to have to get good with it, right, to be able to figure out what's going wrong with your programs. Any questions before we get into our next set of topics, talking about how to translate common blocks of C code into assembly?
A question about Unix system.
Mm-hmm.
So if I'm using a Mac, can I just connect to the CSI computer by using Windows, or I have to like a new operating system?
So all you need is access to a Linux operating system. So if you connect to the CSIF, they're running Linux, and so you're good. You could also run your code on Mimir, right? You don't have to install like a virtual machine at all. You can just open up the Mimir IDE and do your programming in there, and you'll be fine, right? If you want to dual boot or you want to install a virtual machine on your own computer, go ahead and do that. Some of the downsides about remotely connecting, though, are you won't be able to use DDD. You'll have to use GDB. And GDB is all text-based. It's all terminal-based. So debugging this program using GDB looks like this. GDB. And one thing that can make it a little bit easier is --TUI for terminal user interface, and then for some .out. And now you're going to have to like go through it using the terminal. And so you can like use the up and down arrows to go through the code, but you have to use all the command lines. There's no GUI interface. So I can say like break it _start, and it's going to set the breakpoint up here at _start, wherever that happens to be at. So you can see the breakpoint. And if I say run, right, it's going to bring me there, and I can keep like stepping through it, and I can see what line of code that I'm on. but I find this a lot harder to work with than working with the DDD.
On Mimir, is there DDD or is
There is, you can't use DDD on Mimir. You can only use GDB.
I had a question
Mhm.
on the EAX stuff.
Yeah.
Is there a reason you split two variables inside two different spaces, or could you have storing one in the lower half and store the other in the upper half?
So your question is like, could I have like, instead of using EAX and ECX, could I have used like AL and AH?
Yeah.
So remember, AL and AH are only 1 byte big, but we have an array of integers. So integers are going to require 4 bytes, right? Which is going to lead to some issues if you're only using things that can only hold 1 byte. But if we knew like our elements weren't going to become unrepresentable, I should say also the advanced indexing mode, like the array access, requires full registers here. You can't use partial registers. But if we had like an array of characters, we could have used something like, AL instead of EAX, or AL instead of EAX, and then we would have used like add B instead of add L. Anything else? Okay. No, that's not what I want. So one of the more common things that you have to do is translate loops. Let me make this bigger. So over here, here's our C code. It might be like while I is less than, right, some value. Do some code, right? So if you're trying to write this, the way that I end up doing it is the first step that I do is I get the negation, or first step I would say would be to mess with the condition. So first, condition must be compared against 0. So that's going to change this to be I minus value less than 0, right? Then I get the negation of the condition, which is going to be I minus value less than or greater than or equal to 0. So the way that we then translate this would be something like this. While start, colon. So we have some label to mark the beginning of our while loop. And then I compare against the negation of my condition. So over here, in the translation, we're going to assume that ECX is I, and value is EAX. Just so that I can actually write you some legal code. So here, the first thing that I need to do is I minus value. So I'm going to do a comp L, assuming these were integers. And then we're going to have %EAX, %ECX. And it might look a little bit backwards, but remember, it's always dest, op, source. So over here, what this is going to be is ECX minus EAX is what gets computed. But in our example, ECX is I, right? So we're going to do I minus EAX, which is value. Notice in our code, we wanted to do I minus value. Then the comparison for our condition is jump if greater than or equal to, because we want to leave the loop if we're greater than or equal to, and we go to the end of the loop. Then what we have down here is here's our code, right? Whatever that happens to be. And then down here, we're going to have the end of the loop. And notice there's a colon here, no colon here. The other thing to note is that these labels are not special. You don't have to name them while start. You don't have to name them end loop. They can be whatever you feel like, but make them something sensible so that you can understand what's going on. Any questions on this translation? So next week, we'll go through more common code translations, for loops, do while loops, if else, and then array accesses. And your next homework assignment should probably be up over the weekend too.
Is it assembly or
It's assembly. Yeah.